Hello everyone, my name is Kevin, and I decided to do my final project on whether or not translational initiation and mRNA degradation can be considered simultaneous processes. I was inspired by this one paper by Hansen and Maike on cytoplasmic amplification or transcriptional noise. And in this paper, they have a model that considers translational initiation and mRNA degradation as mutually exclusive processes. And many models do this because it is a reasonable assumption that simplifies calculations. But I wondered whether or not they were actually mutually exclusive and whether or not there were a significant difference in any sort of output if they were considered as processes that could occur simultaneously. And this is relevant specifically to this paper because the cytoplasmic amplification of transcriptional noise that they did observe is potentially explained by these two processes not being mutually exclusive, as in translational initiation and mRNA degradation could occur simultaneously. This is because it adds additional steps through which noise can be introduced, and also through the ribozyme cleavage system for uniform translational start sites. If the transcript begins to degrade while translation is still occurring, the start site of translation may no longer be uniform across all transcripts. So to simulate this system, I designed a two-part reporter system under the Lackey inducible promoter. And this construct has RFP on the N terminus and GFP on the C terminus. And so the transcript would have the RFP gene on the 5' end and the GFP transcript on the 3' end. And the idea is that if translational initiation and degradation are not mutually exclusive, then I will consider the formation of truncated mRNA. And degradation can occur from either the 5' end or the 3' end. And from the 5' end, it would eat into RFP, and from the 3' end, it would eat into GFP. And after allowing the system to reach steady state, I would plot the ratio of fluorescence of RFP over fluorescence of GFP, or rather concentrations of RFP over GFP, and observe whether or not the ratio is equal to 1. And if they are equal to 1, then RFP and GFP should be equal in the cell, and there would only be full transcripts. However, if this ratio is not 1, this indicates the presence of truncated mRNA, because as the mRNA degrades from the 5' end, RFP will be affected, and as it degrades from the 3' end, GFP will be affected. And as I said before, measuring this ratio should give me 1 if the concentrations of RFP and GFP are equal in the cell, which is to say that translational initiation and mRNA degradation are mutually exclusive. One does not affect the other. And in the case that they are not mutually exclusive, this ratio should not equal 1 because the concentration of either RFP or GFP will be affected. And some assumptions that I made were that the fluorescence of a protein disappears only when it is entirely degraded. And in reality, the fluorescence likely disappears as soon as the chromophore is affected, as in the codons coding for the chromophore residues on the transcript begin to degrade, but this was too difficult to simulate. And I will also assume that 5' degradation and 3' degradation do not occur simultaneously. And although this is possible, it is again too difficult to simulate and beyond the scope of my model. And the parts of the mutually exclusive case would be full mRNA and the concentrations of RFP and GFP over time. Now, the full mRNA should produce equal amounts of RFP and GFP, which leads to this ratio that I mentioned before being 1. And the concentration of full mRNA will depend on the amount of inducer that I spike in. In the not mutually exclusive case, there are 2 extra parts added in to account for truncated mRNA being produced and translated. As you can see, the RFP and GFP parts now have additional translational addition terms in order to account for the translation of the truncated RNA. And the 2 new parts involve fractions of degradation of the full mRNA to create truncated RFP, which is the mRNA that produces RFP but not GFP, so 3' degradation, and the mRNA truncated producing GFP, which is 5' degradation, as in it does not produce RFP. And after simulating the system for the mutually exclusive case, I produce a graph as expected with a ratio of 1 across all time points. This makes sense because with only full mRNA transcripts to consider, the ratio of RFP to GFP should be exactly the same because each full mRNA transcript will produce equal amounts of RFP and GFP, assuming that translation occurs completely for every transcript. And to verify this, I also plotted the concentrations of RFP and GFP over time individually. And as you can see, the graphs are exactly the same. So the ratio is still 1. And in the not mutually exclusive case, considering truncated mRNA, the ratio actually decreases from 1 to about 0.38, and it remains constant, which makes sense because these concentrations should reach some constant value at steady state. And looking at the individual concentrations of these fluorescent proteins, it seems that RFP has a much lower concentration than GFP. Although at 0, there should be a jump to this constant value of the ratio because both RFP and GFP will start at 0. But this time point of 0 is not quite as important in my consideration. And the increase in slope at the beginning also corresponds to the ratio, surprisingly, of about 0.38. So to conclude, after running these simulations, there can be a difference in output when considering that translational initiation and mRNA degradation are not mutually exclusive. And based on the ratio of RFP to GFP in the not mutually exclusive case, it actually seems that 5' degradation is more prevalent because this reduces the amount of RFP that is created. And the ratio should be a good representation of 3' degradation to 5' degradation, being related by about a ratio of 0.38, which was the ratio seen in that graph previously. And some future experiments would be to repeat these simulations, but without fluorescence as a reporter, as fluorescence is not the best measure of transcript activity because it can be delayed by the time taken to translate the transcript. And because of this delay, it is not a direct measure of the transcript, but rather the product of the transcript. So a possible procedure to perform is global RNA-seq to get a sense of the types of transcripts in the cell. And thank you very much. Hope you enjoyed the presentation.